Now, let's start off our analysis of floating point precision by looking back to some of the sources of where it started. In 1936, Alan Turing wrote an article, a paper, that really started the computer revolution. He, of course, is the inventor of the Turing machine, the kind of source of a computational machine that we now utilize for in our computers. He defined a computable number in a slightly archaic way, but it relates to the idea of having a finite representation. And more specifically, is a real number which can be represented by a finite number of digits in the machine's number system. Now, the Turing machine was base 2, and most of the computers today are binary, base 2. However, a couple of them do exist that work with different bases. We'll ignore that for now. Base 2 representation is a little bit different than decimal interpretation. For example, the number 0.1 or 1/10 is not a computable number. Base 2. Even though it is computable base 10, we just don't work with computers that are base 10. Since 0.1 can be rewritten as an infinite series. K equals 1 to infinity of 1 over 2 to the 4k plus 1 over 2 to the 4k plus 1, which is the sequence of binary digits 1, 1, 0, 0, and then next bit 1, 1, 0, 0, next bit 1, 1, 0, 0, repeated on and on and on and on. Now, because we have an infinite representation base 2, to write down the number 0.1 or even computing with the number 0.1 requires there to be some round off error. So we approximate non-computable numbers by their closest floating point value. So let's look at how we represent a floating point number. And it all comes back to scientific notation. The idea that you want to represent every number in terms of a common range of initial values times the base, usually base 10, and for scientific notation, base 2 for us, times the base raised to the exponent. So here is the common floating point representation that can be used to store every computable number. We have the sign, one bit of information, a fractional part, or sometimes called the mantissa, which represents how precise we can be to represent that number, how deep down we can approximate that real number with rational numbers, rational expressions. And then the exponent, how big or small, what's the range of numbers that we can represent. And of course, the 2 is the base. So here is that modified scientific notation I was talking about. In scientific notation, we usually use base 10, but of course, this is working with computers, so it's base 2. An example of using this floating point form is the standard double precision. By standard, I mean the 1985 national standard put forward by IEEE, the Institute for Electrical and Electronics Engineers, as well as ANSI, the National Standards Institute, American National Standards Institute. This was a large process to get all the machine manufacturers to agree to produce computers that all represented numbers in the same or very similar way, so that we could expect the same kinds of errors and error propagations from every machine. The standard can be quantified in terms of a 64-bit number X in binary, of course. And those 64 bits are broken down into the sign with 1 bit, fraction with 52 bits. That, of course, is the precision, how close we can get to a number. Now, binary bits represent integers, and because we're dealing with a fraction, we just take those bits and we shift them to represent fractional pieces instead of integer components. But it's the same idea. Then, the exponent with 11 bits. And again, that is also shifted. Now, what do I mean by shifted? Well, that means that the fraction f can be scaled up to an integer 2 to the 52nd power times f is going to be greater than or equal to 0. It could be 0 if you're dealing with just a multiple, a power of 2. Or it'll be less than 2 to the 52nd power, because the fractional part is going to be less than 1 itself. And the exponent is shifted by 1023. Is bounded above 1 and below 2 to the 11th minus 2. Looking at the 11 bits for the exponent. And the extreme ranges of the exponent are used for specific types of special numbers. So most of the time we're within those boundary limits. And this range, 2 to 52 times f, and e plus 1023 are both positive integers. So that's why we shifted up. Positive integers. Since e itself, the exponent, can range between since e itself can range between negative 1022 and positive 1023. There we go. Yeah, so we just added part. Yeah. Thanks. Now there is also single precision and quad precision and variable precision that have different values for the sign, fraction, and exponent bits. And you can test your machine to determine what kind of precision it has. So you can test your calculator, you can test your phone, you can test Google spreadsheets, Excel, you can test Matlab, you can test various other calculators to see what their machine precision is. And one way we can define that across all of machines is by what's called the machine epsilon. I mentioned before that there are some errors between the numbers we can store and the real numbers that actually exist. There are actually different kinds of errors. You can have an overflow. You can have a number too big and goes towards infinity. And the negative sense of becoming too close to zero, underflow. So you have overflow and too big of a magnitude towards positive or negative infinity, and underflow, too small of a number, too close to zero. Those we'll see every once in a while, but the quantity we want to track, and the one that's most easiest for us to track, is the machine epsilon that represents the round off or precision of our error. Every machine's precision can be measured based upon the distance from 1, the number 1, or 2 to the 0, first bit, to the next biggest floating point number. So in a sense, we have the number 1, we have the number 2, we have somewhere in between there, here's 1/2, here's 1/4, and right in there is the gap, the machine epsilon, between the number 1 and the next computable number, right there. for IEEE double precision, apps is defined in binary as 2 to the negative 52nd power. Why? Because our precision utilizes 52 digits. So then the closest we can get is 2 to the negative 52nd power. Now this value, that'd be 2.2204 times 10 to the negative 16, essentially 16 digits. We have precision to about 16 digits, which is the maximum relative round-off error. Maximum relative round-off error. How far off you could round to be. And the book mentions that if you're rounding off at an error of epsilon, then you could round it to the left or to the right, and so your full gap is actually 2 times epsilon. But we'll just stick to epsilon itself as the round off. That wraps up our definitions. We'll now move on to some demonstrations of examples on how we can identify error with various machines or utilizing some iterations.